last we met, we were discussing, or we just started discussing, universal and existential statements. When it comes to quantifiers. Going to get into bounded variables, the bound variables and scope, variable scope. Consider the following two statements. For all integers, x, element, integers, x squared is greater than or equal to 0. Okay? And there exists an x, there exists an x element of integers such that x cubed equals 8. Now the variable x is used in both statements, but they have served different functions. We say that the variable x is bound by the quantifier that controls it, and that its scope begins when the quantifier introduces it and ends at the end of the quantified statement. It's kind of like having a variable in a function in C++. The scope of the variable is limited to the function that it is declared in. And it is only when it is declared, it begins its scope, and then at the end of the function, it goes out of scope, and you can no longer access that variable. The same is true for the quantified statements. X is bound to this quantifier. There exists existential quantifier for the duration of the statement. And therefore, this statement can also exist in such a with a different use of the same variable. All right. Implicit quantification. If a number is an integer, then it is a rational number. It is a universal statement without the telltale word all or every or any or each. The indefinite article a is the only indicator. So, I need my glasses for this. Implicit quantification. The notation, say P of x and Q of x are predicates, and suppose the common domain of x is D. The notation P of x, Q of x, what that actually means, that every element in the truth set of P of x is in the truth set of Q. Or equivalently, for all x, P of x implies Q of x. The notation with the double arrow, P of x, Q of x, means that P of x and Q of x have identical truth sets, or equivalently, for all x, P of x, biconditional Q of x. Now, when you get into the slides, that's about it for implicit quantification. When you get into the slides, there is a program that was developed that they talk about called Tarski's World. I choose not to use that as an example in class because it's cumbersome to have the slides and going back and forth between what they're talking about and the diagram that is given in the first slide and all that sort of stuff. So it gets kind of cumbersome following what it's doing in the slides. But if you wish to learn more about logic and the Tarski's World program that teaches logic, feel free to go through the slides. It comes up occasionally within the slides, but I leave that to you to look at the slides to learn more about Tarski's World. Okay. Negations of quantified statements. Negations. All right, so if you have for all x in D, P of x, and I have Q of x, the negation of that, so taking the negation of that is there exists, and I keep doing that, there exists an element x, element of D, in D, such that not P of x. The negation of a universal quantifier is an existential quantifier. This is the case without respect to predicates and the domains of the predicate variables. So basically, if P of x is true for all elements of x in D, the negation of that means that there exists at least one element of D, x, such that P of x is not true. So you have that negation. Negation of a existential statement. So there exists an x in D such that P of x. There's at least one element of D for which P of x is true. The negation of that The negation of that, if this would write, would be for all x elements of D, not P of x. That means there's no element in D for which P of x is true. Go ahead and put the line here to indicate there's a separate concepts there. So the negation of an existential statement is logically equivalent to a universal statement. So for the negations of the following statements, for all primes P, P is odd. The negation of that would be there exists a prime that is not odd, which happens to be the true statement because 2 is a prime and it's not odd. So let's see here, another example. There exists a triangle. There exists a triangle T such that the sum of the angles, such that the sum of angles of T is equal to 200 degrees. The negation of that would be for all T elements of capital T, sum of angles is not equal to 200. Now I wrote these out formally, but care must be taken to avoid mistakes when writing negations of statements that are given informally. One way to avoid mistakes is to write them formally and then negate them. What about the statement, no politicians are honest? I think that from our first chapter, that was a tautology, always true. No, never mind. So no politicians are honest. Formal version. Write it out formally. For all P elements of P, P is not honest. Okay? Well, the negation of that would be an existential statement because this is a universal. There exists a politician P such that P is honest. Informal version of the negation, some politicians are honest. I'll leave that to you to figure out whether the original or the negation is true. But negations of universal conditional statements. Negation of universal conditional statements. The form of negations of universal conditional statements can be derived from facts that have already been established. So, of universal conditional statements. Let me go ahead and write that. Negation of universal conditionals. Okay. So, we have, for example, for all x, if P of x, then Q of x, and then negate that. I have an extra. Negate that. Now, what we already covered is a negation of a universal statement is an existential statement. So, it would be there exists an x such that not P of x implies Q of x. Okay? Yeah. Okay. But we learned previously the negation of a conditional, a regular conditional, is P of x and not Q of x. If you look back in your notes, you'll see that there somewhere, hopefully. So the negation of the universal conditional is there exists an element x such that P of x and not Q of x. Going from here to here was, I believe, chapter 1, right? Or was it chapter 2? In chapter 1 or 2. But when we first got into truth tables and stuff. Okay, what is the negation of the following statement? For all persons P, if P is blonde, then P has blue eyes. The negation would be there exists a person that has blonde hair but does not have blue eyes. So, and the same could be true with existential statements. The negation of an existential conditional would be a similar mechanism. Although the slides don't cover that, I guess. So, Okay. Now the relationship among the universal quantifier, the existential quantifier, and or, the negation of a for all statement is a there exists statement, and vice versa. These facts are analogous to De Morgan's law. The negation of an and is an or, and vice versa. So, a universal statement is a generalization of and statements, and existential statements are generalizations of or statements. So, there, for all x element of D, q of x 0, and q of x1 and q of x2 and so on and so forth. It is true for all of the predicates when you add, when you do the and of each element in D. That would be for all x is the element of D. Now, there exists would be more akin to a or statement. There exists an x in D such that q of x0 or q of x1 or q of xn. There exists an element of D such that q of x1 is true, or q of x2 is true, or q of xn is true. There exists at least one of them is true. That would be a sequence of or statements. So if you have a finite set of a finite set for the domain, you can show truth by example here, or you could prove this by exhaustive demonstration of all that q of x is true for all elements of D. All right, vacuous truth. Of universal statements. Okay, consider the statement that all the balls in a bowl are blue, when in fact there are no balls in the bowl. Is the statement true or false? It is only false if and only if its negation is true. The negation is there exists a ball in the bowl that is not blue. So let's look at this formally. Let's see here. Let's see here. No. I didn't put out the. Well, anyway, the negation of the balls, all the balls in the bowl are blue. The negation is there exists a ball in the bowl that is not blue. But the only way for the negation to be true is that for there actually to be a non-blue ball in the bowl, and there is not. So the negation is false, and the original statement is true by default. In general, A x in D, P of x implies Q of, if P of x, then Q of x, is called vacuously true if P of x is false for every x in D. True if for all x in D not P of x. That would be vacuously true, a vacuously true statement. This, true if and only if. Now, there are variants to the universal conditional statements. The contrapositive. So you have your original statement for all of x, element of D, P of x, then Q of x. The contrapositive would be for all of x, element of D, not Q, if not Q of x, then not P of x. And we learned before that the contrapositive is equivalent to the original statement, logically equivalent. So that's the contrapositive. Then you have the for all of x in D, Q of x, then P of x. That's the converse. And then you have the inverse, which is for all of x, element of D, not P of x, then not Q of x. And that's the inverse. So take this, how about the different versions of the following statement? If a real number is greater than 2, then its square is greater than 4. So a of x, element of R, if x is greater than 2, then x squared is greater than 4. The contrapositive. If the square of a real number is less than or equal to 4, then the number is less than or equal to 2. Contrapositive. Equivalent statement. Converse. If the square of a real number is greater than 4, then the number is greater than 2. Which is not true. It's not the equivalent statement because -3 is less than 2, but has a square greater than 4. The inverse. If a real number is less than or equal to 2, then the square of the number is less than or equal to 4. Again, this is not true because -3 is less than or equal to 2, but the square is greater than or equal to 4. So the converse and inverse are not equivalent statements to the contrapositive and the original. All right. The converse and the inverse are not the same as the contrapositive and the original. But the contrapositive is another way to say the original statement. All right. Necessary and sufficient conditions. Okay. So a sufficient condition, so say for all x, R of x is a sufficient for S of x it means for all of x R of x, if R of x, then S of x. A necessary condition is for all x, R of x is a necessary for S of x. That means for all of x, R of x, I'm sorry, not S of x, then not R of x. Am I getting that right? Yeah. which are basically the same thing. This is just the contrapositive of this, but the wording is just a little bit different, that's all. So each of the following statements as a universal conditional statement, without using the word necessary or sufficient. Squareness is a sufficient condition for rectangularity. If it's a square, or if a figure is a square, then it is a rectangle. Right? Being at least 35 years old is a necessary condition for being President of the United States. For all persons X, if X is less than 35, then X cannot be President of the United States. Or, for all persons X, if X is President of the United States, then X is at least 35 years old. All right. So, just different ways of saying the same thing. Statements with multiple quantifiers. Actions suggested by the quantifiers are performed in the order in which the quantifiers occur. So, for example, for all X in D, there exists a Y in D such that P of X and Y is true. Satisfy the property P of X. Why? Oh, this does not have to be the same. This does not have to be the same. It could be element of E. Y could be an element of a different set, a different domain. To show that the statement is true, you must show that for every element in D, there is at least one element of E that satisfies the property. Because you do not have to specify the second element until after you choose the first element, you are allowed to have a different second element for each of the first elements you choose. Again, the slides get into Tarski's world and demonstrate, have an example to demonstrate this concept. And then there's the opposite, where there exists an X element of D, and for all elements Y of E, P of XY. Now here,
You have to find one particular x and d that will work no matter what y in E anyone might choose to challenge you with. So there exists an element in D where there's for all elements of E, P of x is true. You can see how that they are quite different in their meaning based on the order in which your quantifiers present themselves. Let's see here. Where is it? There was a example. Now, you're going to have a little bit more complex example. Okay. Cafeteria line has 4 stations. All right. Salad, which has green salad and fruit salad. Main dish, which is fish or spaghetti. A beverage, which is what are the beverages they give? Milk, soda, and coffee. And then dessert. Not dessert, which is pie or cake. Now, one student had the green salad, spaghetti, pie, and milk. Green salad, spaghetti, pie, and milk. Another student had fruit salad, fish, pie, cake, milk, and coffee. Fruit salad, fish, pie, and cake, and milk, and coffee. And then the third student had spaghetti, fish, pie, and soda. Fish, spaghetti, pie, and soda. All right. Which of these statements are true? There exists an item I such that all students S chose I. Is that true or false? Is there an item such that all students chose it? Yeah, pie. So it is true. There exists at least one item. There exists a student S such that S chose all items. There is a student that chose every available item? No, that's false. There exists a student such that all station Z and E, there exists an item I in Z such that S chose I. Is there a student that chose at least one item from every station? Yeah, the red one chose one item from every station. And how about every student chose at least one item from every station? No, green didn't take from the salad station. So that one would be false. And for all students S and all stations Z, E, there exists an item I in Z such that S chose I. For all students, chose at least one item from all stations. False, yeah. Nobody took everything. Or all students didn't take one item from every station. All right, let's see here. Revisit a topic from before. Translating from informal to formal language. Problems are often presented in informal language. Solving them requires translating them into formal language. Redo the following statements in formal language. Every non-zero real number has a reciprocal. So for all x element of non-zero real numbers break it down into different parts. Every non-zero real number there exists there exists a I'm sorry. There exists a y such that y is the reciprocal of x. That's a little bit more formal. The slides have it put it a slightly different way. For all there what is it? For all non-zero real numbers U, there exists a y, or a v, there exists a v, element of real numbers, such that u b equals 1. How about there is a real number with no reciprocal? There exists a x element of R where all y element of R x y does not equal 1. Such that there exists an element x, there exists an x, which is a real number, such that there, for all real numbers y, x times y is not equal to 1. Translating informal language into formal language allows you to prevent ambiguity. It is clear with the symbols used and the language used what you're meaning and the truth or falsity of the statement. Let's see what time it's going to be. Oh, still got plenty of time. All right. Just copying things down. Let's see here. Negation of multiple quantifiers. You can use the same rules to negate statements with several quantifiers that you use to negate simpler quantified statements. So, for example, the negation of for all x in D, there exists a y in E such that, let's see here, P of x, y, and close parentheses there. Okay. This, you would, for all elements of D, there exists a y in E where P of x, y is true. The negation of that is there exists an x in D such that for all y in E, not P of X, Y. You flip the quantifier from universal to existential, existential to universal, and then you invert the predicate. Take the negation of the predicate. The slides use another Tarski's world example, and you can pursue that one as you wish. The order of quantifiers is very important. Consider the following statements. For all X element of persons, there exists a Y, also an element of persons, such that X loves Y. Okay. Pretty simple statement. Now consider there exists an X element of persons such that for all Y, X loves Y. The order of the quantifiers changes the meaning of the statements greatly. If the quantifiers are of the same type, the meaning of the statement does not change with the order of the quantifiers. Whereas the predicate is the same, X loves Y. For all X and P, there exists a Y in P such that X loves Y. So basically, informally, everybody loves at least somebody, at least one person. Okay. The second statement, there exists an X in P such that all Y in P, X loves Y. So there exists a person that everybody loves. Two totally different meanings, two statements with totally different meanings, just because the quantifiers are flipped. So the order of quantifiers is very important. Now, I've been using as much symbolic notation as I can, primarily so that you get used to seeing it. In some areas, logical statements are expressed in purely symbolic notation. The disadvantage of fully formal notation is that because it is complex and somewhat remote from intuitive understanding, when we use it, we may make errors that go unrecognized when we make the translation from informal language to formal language. The advantage is operations can be made completely mechanically. The symbols for quantifiers, variables, and predicates and logical connectives make up what is known as the language of first-order logic. So these symbols make up a language. Thinking about languages, there's a language out there. I don't know if has anybody ever heard of the programming language Prolog? No? Maybe heard of it? Okay. I'm not programmed with it. It's a difficult language to program with. I learned how to use it a long time ago, a particular flavor of it. But Prolog stands for, is short for programming in logic. The slides give an example of programming in Prolog. It is a fascinating language. All the statements are logical statements. It doesn't have your typical for loops or while loops or anything like that. Everything is expressed as a logical statement. What makes it confusing is it can go back on itself. It doesn't just flow one direction. So the logic stream can be kind of spaghetti-like. My father, who was teaching programming at University of California, tried to learn it, and he couldn't get it. I guess I was a younger and more flexible mind at the time. It's like teaching a foreign language to a youngster. It came easier to me because I was younger, I think. But it's an interesting language to use if you're doing pure logic and that sort of thing. But I don't know who makes compilers for Prolog anymore, so okay, I think we're going to call it a day here. We will pick up with arguments with quantified statements on Thursday. Again, I put the deadline for the homework back till Tuesday. Next Thursday, we'll have our midterm exam. So we'll probably finish up chapter 3 on Thursday, do a review session on Tuesday, and then the midterm exam on Thursday. So have a good day.